Thank you. It is a pleasure to be here today, and it's wonderful having had the chance to hear great papers on getting into space, surviving in space, eating and excreting, to be able to talk about coming back home again. And I'd like to begin my story with an historical event. In November of 1968, barely weeks before the crew of the American spacecraft Apollo 8 completed the first trip by humans around the moon, the Soviet Union launched from Baikonur Cosmodrome a capsule modified for piloted flight into deep space. On November 12th, Zond 6 reached the vicinity of the moon, but on its return to Earth, the spacecraft depressurized and, following the premature deployment of its main parachutes, exploded upon landing. Fortunately, no one was on board. On 3 other Soviet circumlunar attempts in 1967, 2 in 1968, and 1 in 1969, launch vehicle failures prevented the Zond spacecraft from accelerating to translunar speeds. During further test flights in 1968 and 1970, computer failures upon the vehicle's re-entry to Earth subjected the Zond to deceleration forces that would have killed any people aboard. On only one flight, launched 2 weeks after the Apollo 11 lunar landing, did a Soviet spacecraft complete a mission that would have returned a human occupant alive from the moon. The capsule, having never proven itself safe for people to fly, was empty. On this, the 40th anniversary year of America's last Apollo flight to the moon, it is useful to remember just how difficult this task was to accomplish. And it is useful to remind ourselves that victory in the race for the moon required the successful operation of an almost incomprehensible number of individual technologies. Of these, none was more important than the technology of speed. Had travel through space required only that humans develop machines capable of reaching altitudes above the great volume of Earth's atmosphere, then the United States would have likely achieved spaceflight shortly after the end of World War II. By 1950, liquid fuel rocketry had made possible the brief attainment of altitudes at which most spacecraft now operate, while research years earlier had solved the problem of keeping humans alive in the vacuum of space. That the orbiting of the smallest artificial Earth satellites required a further 10 years investment in technology reflects the fact that the pursuit of space travel was less a quest for height than one for speed. Astonishing, unprecedented, unparalleled speed. A 30-fold increase in the fastest speeds humans had experienced up to that point. It was only by achieving these speeds that spacecraft would attain orbit, traveling fast enough to coast around the curvature of the Earth without additional propulsion. Throughout the history of space exploration, the most deadly portions of any spaceflight, accounting for 100% of in-flight fatalities, have been those associated with rapid changes in speed. While launch can be perilous and terrifying, it is a spacecraft's return to Earth that has been associated with the greatest number of fatal failures. Spacecraft in Earth orbit must reduce their speed from 18,000 miles an hour to 0 in a matter of minutes, while steadily descending through the atmosphere. Contact with the air heats these craft to temperatures of thousands of degrees, melting spacecraft not designed to survive such conditions. There is a saying among combat pilots that speed is life. For astronauts, though, speed is death. It is speed, not altitude, that kills the crew members of the fictional moon-bound spacecraft in 1950's rocket ship XM. First, a propulsion miscalculation sends them hurtling unexpectedly into the angry clutches of belligerent Martians. Then a fuel shortage on their return to Earth prevents them from safely decelerating their craft before impact. Cracking the technology of speed, both of the acceleration necessary for orbital injection and the deceleration required for deorbit and safe return to Earth, was the foremost technical problem of the space age. Having entered the space race in 1957 with little hardware optimized for that purpose, the United States, within a decade, developed a system of technologies. Launch vehicles like Thor, Atlas, Titan, and Saturn, and upper stages like Agena and Centaur, necessary to propel vehicles at the speeds necessary to achieve Earth orbit, reach the moon, and explore the solar system. At the same time, advances in computing made navigation practical at high speeds. Advances in propulsion and flight control systems enabled the complex maneuvers required for flight into Earth orbit. And advances in structures and materials made possible the fabrication of vehicles able to endure the fantastic accelerations required for spaceflight, while protecting their delicate human occupants from shock, micrometeorite damage, and extreme heating. If there was one difference between the very first artificial Earth satellites of the late 1950s and the piloted spacecraft to follow, it would not be their size or speed, but the fact that the latter would have to come home. Living and working in space presupposed that those who volunteered for this dangerous work would be able to return home alive. In 1957, it was not yet clear how the United States might achieve this feat. The launch vehicles necessary to place humans into Earth orbit could be created by clustering or scaling up existing rocket designs, but technologies for re-entry would be new. In the weightless vacuum of Earth orbit, would America's first astronauts be able to turn a spacecraft, slow it down, and pilot it through Earth's atmosphere, enduring temperatures of thousands of degrees, only to find themselves hurtling at hundreds of miles per hour toward the sea? Inventing space brakes proved one of the most challenging aspects of spacecraft design, and one visible to the larger public only when it failed catastrophically. These inventions required the solution of knotty theoretical problems, but they resulted in devices of enormous practical benefit. And like the best inventions, re-entry technologies were both anticipated in science fiction and were ultimately the products of individual genius. America's early, secret lead in this technology ensured the success of Project Apollo. One can find in the National Air and Space Museum's own collections examples of these technologies. In fact, of all the space-related topics we could discuss today, few would be more appropriate to a Smithsonian Symposium on Invention. Significant funding for the creation of re-entry technologies came from the Smithsonian, which, for the modest investment of $100,000 80 years ago, can justly claim the credit for the invention of both the liquid fuel rocket and the ablative heat shield. The man responsible for both of these innovations was Clark College professor Robert Goddard, who not only built and flew the first modern rocket, but theorized how a vehicle capable of exploring space might return intact to Earth. A craft need not be decelerated by rocket in order to make its descent. Instead, Goddard wrote, friction from Earth's atmosphere could slow the craft in the same way that it slowed the arrival of meteorites that regularly pummel Earth. A hard, thermally non-conductive shield would protect the craft from the extreme heat it would encounter. Goddard also noted that meteorites underwent a, quote, chipping or cracking process as they heated up. This phenomenon protected meteorite interiors by absorbing and carrying away excess heat. Futurist Edward Smith described such an ablative heat shield in his 1934 Amazing Stories serial, Triplanetary, as a material that would absorb and remove heat by a gradual wearing away, one molecule at a time. Like most good ideas, though, this one lay dormant for more than 2 decades before being successfully put into practice. In October of 1957, the Soviet Union startled the world press with the successful orbiting of Sputnik, the first artificial Earth satellite. While the launch also demonstrated that the Soviet Union possessed a reliable military missile with intercontinental range, the Soviet team had failed at that point to develop a warhead or spacecraft capable of returning to Earth intact. The dummy warheads on a series of test launches of Sputnik rockets, as well as Sputnik itself, broke up in the atmosphere, rendering the vehicle useless as a weapon system. When the Soviet Union launched the dog Laika into Earth orbit the following month, as we heard, it did not recover her, not because it didn't want to, but because it couldn't. It was these rockets that could go up, but could not come down, that Soviet rocketry pioneer Sergei Korolev used for his satellite program. Quote, the flight design testing program of the first series of R-7 missiles showed that the structure and heat shield of the nose cone disintegrated during entry into the atmosphere. TASS's August report about the production of an intercontinental missile was a bluff, in the sense that the missile had no warhead. but aside from the very few of us who were privy to the secret results of the flight tests, no one knew. The United States would not match Sputnik's accomplishment for many months. Prior to the Soviet Union's successful launch of Sputnik, though, the United States Army had recovered an American nose cone that during a previous rocket test had survived the frictional heating of high-speed re-entry into Earth's atmosphere. The experiment, which President Dwight Eisenhower disclosed on national television after Sputnik's launch, proved the feasibility not only of warhead re-entry, but of the safe return from orbit of reconnaissance capsules and piloted spacecraft. What had made the cone special, and I hope everyone strolls a few hundred feet over to take a look at this particular artifact right here in the museum, what had made it special was both its shape and its covering, a phenolic resin that vaporized molecule by molecule during the frictional heating of re-entry. Without such a shield, the nose cone and the nuclear warhead it might have carried would have melted in the lower atmosphere before reaching its target. The United States had not yet launched a satellite into space, but it had effectively recovered one. The USSR won one leg of the space race, but the United States had won the other. Contemplating his mortality in the 1975 film Love and Death, Woody Allen declares his intention to, quote, run through the valley of the shadow of death, because you get out of the valley quicker that way. For many years, this was the way in which missileers contemplated re-entry of vehicles through Earth's atmosphere. A narrow re-entry vehicle would endure minimal heating through most of its journey through the upper atmosphere, enduring brutal temperatures only briefly as it fell through the thicker air closer to Earth's surface. An ablative heat shield would reduce that temperature to tolerable levels. Warheads, though, were not people. Such a craft could still get too hot for humans to fly in. It was National Advisory Committee on Astronautics engineer H. Julian Allen who, in 1953, turned conventional wisdom on its head by arguing that a decidedly unaerodynamic blunt craft that heated gradually throughout its flight and was protected from frictional heating by its own shockwave offered the lowest rates of heat transfer. Pairing a blunt body re-entry capsule with an ablative heat shield would enable the construction of a craft cool enough for a human to fly in. Without careful nurturing, even great ideas will fail, though. Fortunately, the blunt body re-entry vehicle had a champion in legendary NASA engineer and manager Max Faget. Faget not only realized the concept's elegance, but defended the downright ugly spacecraft it required against scores of aeronautical engineers who preferred that America's first space vehicles look and fly more like airplanes do. Instead of sailing into orbit and back on wings, the Mercury spacecraft would be hurled into orbit atop a computer-controlled rocket. At the conclusion of the flight, the pilot would fire 3 small solid rocket motors in the opposite direction of the spacecraft's motion, which would slow the craft down just enough to leave orbit. Gravity and the craft's ablative heat shield would do the rest. For the pilot, the ride would be rough, warm, and lonely, as the ionization of hot gases around the descending craft would block radio transmissions. But the spacecraft would survive, and so would its pilot. Optimized to survive re-entry, the Mercury spacecraft would offer its crews neither wings nor landing gear. Instead, the capsule would plummet through the atmosphere and land at sea via parachute, a kind of arrival that pilots associated with failure and not success. If problems occurred during launch, Mercury astronauts had some means of escaping their launch vehicle. During descent, though, there was no backup system or means of escape. The system, though, worked and could be perfected more quickly and more cheaply than any other. In time, additional modifications might even allow astronauts to steer the craft during re-entry, providing them with some measure of control over the most dangerous part of their mission. America's larger two-person Gemini spacecraft of 1965 was constructed with the ability to use its blunt-bottom surface to create lift. Combined with an early digital computer produced by IBM that could fire rocket thrusters with speed and precision, the innovative craft enabled astronauts to control their descent and achieve a more precise landing. The techniques and technologies developed for Gemini proved vital to American astronauts' safe return from the moon a few years later. The Apollo lunar program brought the issue of deceleration to the forefront, as designers realized that a spacecraft returning from the moon would be traveling so fast that its impact with Earth's atmosphere would likely produce fatal shocks for its crew. Apollo's spacecraft returning from the moon would strike Earth's atmosphere at such speeds that delicate maneuvers would be required to slow the craft down and shed the enormous heat that would be produced. A blunt body shape, an ablative heat shield, a lifting double-dip re-entry controlled by a sophisticated computer would all be necessary to achieve the required trajectory. These technologies made lunar flight possible and remained a source of difficulty for the Soviet space program. It is fitting that one of the final photographs taken of an American space shuttle in flight, and possibly the most significant one of the entire mission, was this startling image from the International Space Station of shuttle orbiter Atlantis' re-entry into Earth's atmosphere. 50 years after the launch of the first humans into space, the United States continues to grapple with the technology of speed required for spaceflight. With years expected to pass before a suitable replacement emerges for the space shuttle, and with the engineering community once again investigating options for delivery of payload and crews to Earth orbit and back, the United States again needs solutions to what has proven to be the fundamental problem of spaceflight, the problem of speed. Solutions developed by America's first space inventors, the blunt body and the ablative heat shield, may just turn out to be the best of all. That these technologies succeeded so well and so often is a credit to the individuals who invented and perfected them. The problem solvers of the 1950s and 1960s were successful in their efforts to master the technology of speed, and their successes defined our notion of space exploration. Thank you.
How do you contrast the role between innovation and invention in each of the technologies that you discussed?
Well, I mean, to me, innovation is more of an idea that, like some of the slides that I shown, can work or may not, and some of them are very odd looking and not necessarily from a practical point of view will finally work, where an invention to me is the practical element that it can be of use.
I must confess that as someone who teaches the history of technology, I'm still not entirely sure of the difference between invention and innovation. I am confident in saying that at least with regard to re-entry technologies, I think we see examples of both. We see new applications for old technologies. One of the heat shield materials that was considered was wet wood, which is actually a really, really great substance to work with. But we also see innovations that are taking an entirely new look at a very old problem and creating a device that's deviously simple in an almost flash of genius, which I think is a lot of people's definition of invention. And we also see room for both large industrial and government laboratories, as well as individuals with good ideas who are able to put them into practice in this very interesting and technically demanding area of scientific and engineering research.
I agree with Matt in terms of there's not a perfect way to define or separate invention from innovation. But I think in my case, one of the things that I find interesting, and certainly this is how engineers think, is there are no simple answers to one problem. And certainly by the time Skylab comes along, the expectations for what is important to an astronaut is changing. And so the solutions that worked fine in the 60s wouldn't work in the 70s, even though we're still talking about food and we're still talking about waste containment. We're still talking about sleeping. Those things evolve as human values change.
Question? Roger?
I've always got questions. Okay, I have one for each. So, Pablo, the issues associated with long-duration missions beyond the Van Allen radiation belts and to the moon and Mars. What is being done, and what are you looking at in the context of EVA suits to ensure radiation hazards are minimized and so forth? Then let me ask the other two questions, and then I'll just step away from the mic. So, Amy, you talked a lot about habitability and its importance for long-duration missions especially. How would you rank this in terms of a scale, issues of habitability and where that sits in terms of high or low priority versus other issues of ease of use, reliability, economy, and so on? And then, for Matt, the best for last, how can we use ice to slow down when we get to Mars and go into an orbit there? I'm being silly, but that is a major issue. How do we when we build a long-duration space mission for humans to go to Mars, one of the key components is actually backing off from the speeds necessary to do that to get into an orbit. And is there ablative heat shield technology, things like that we can use in the process? Anyway, you've each got a question.
Okay.
Thank you.
I can start. Right now, we know for sure that humans can survive in space for the duration of a trip to Mars with chemical propulsion, because Valery Polyakov, some years ago, I don't remember the record, I think it was 470-something days. So we know that the body adapts enough for a long-duration spaceflight. Now, one thing is being inside in the low Earth orbit, and a very different one is being traveling to the moon or Mars, where, of course, we have the radiation problem. From the spacesuit point of view, there is no way to protect the astronauts. I do think that radiation is probably the biggest problem that we face when we talk about long-duration spaceflight. I suspect that the protection will have to come from the spacecraft, not the suit, because so far we couldn't find a solution to protect the astronauts of radiation. I examined the subjects, and there are a number of researchers who are working actively on this. For the structural systems of the spacecraft, and I do think that that's the single most critical factor for a continuous trip to the moon or a single trip to Mars. But yeah, there is no solution yet for the spacesuit part.
Roger, I'll talk specifically about psychology versus economy. Because I think that's as much the issue as anything. Some of the equipment that's being developed that human factors engineers think are important for improved habitability are heavy, and certainly anytime you add weight to a launch vehicle, the cost goes up, and that seems to be one of the major concerns. But with long-duration flight, psychology has to become more important. The negative aspects of being away from home, really away from home for 6 months, 3 years, those factors will take more importance. But one of the things that has always been, I think, a struggle for engineers is thinking they know the solutions, thinking they know the best ways, but this will have to be a conversation not only between the astronauts about the engineers about what is possible, but also with the astronauts and what they are prepared to tolerate and live with and what those expectations are. Certainly, engineers have made decisions, habitability decisions, that the astronauts said, yeah, we don't really care. And certainly that's the situation with the hot bombs. But I think NASA is understanding that the psychological aspect of being an astronaut has to be a part of the discussion, and it will be a balancing act. That is the reality of all engineering, is it is a balancing act.
In answer to your question, Roger, yes, ice is nice. As is iron, if it weren't so heavy. Certainly it protects meteorites. And I think it's a very good question because it reminds us that probably the unsung form of innovation when it comes to space technology may be in material science. We are living in a world filled with materials that didn't exist 50 years ago. And creating materials with all the properties that we need for these demanding missions is quite challenging. The ablative heat shield made out of the phenolic resin was very successful. The shuttle used a very different technology, which, while perhaps even better at heat resistance, was more vulnerable to physical damage. And so we see the trade-offs involved in using these different technologies. And for the case of Mars, we're talking about something that's going to have to be packed up and work a year later, maybe more. Something that will be light enough because fuel is at a premium, and something that's going to be 100% reliable. I know some of the technologies people have discussed have included inflatable structures, which could act as shields and take advantage of atmospheric drag to perform that orbital insertion. One thing I can guarantee is that bag is probably going to be made out of a material we haven't discovered yet, because this is a field of dynamic and interesting research in which there's still plenty of opportunity to learn how to do things a new way.
Good afternoon. I have a relatively open-ended question.
Identify yourself, please.
Robert Thomas, pretty local actually, down in Northern Virginia.
Mm-hmm.
Basically, as I said, it's kind of an open-ended question. What do each of you see as being the key innovations that need to move forward in order to expand human activity in space in terms of duration, in terms of quantity of people, and in terms of the different kinds of operations and environments that we're working in? Pick whichever highlights you would like to talk about.
I think radiation protection is going to be key, certainly as we're traveling through space. That is one of the issues that we're really struggling to solve, and that will be a priority. You cannot protect an astronaut's health if you cannot protect them from radiation. I think the other thing is sustainability, not only in terms of funding a program, maintaining the support systems on the ground, but as we move further and further away from an environment we generally understand on Earth, how do we keep a flight going for 3 years? How do we keep a flight going for 10 years? How do we keep a colony going? And developing some of those concepts that we're struggling to do even on Earth are going to be some of the greater challenges.
And I think that we have to look to our ability to begin to manufacture materials on the atomic scale, because one thing that we do need to do is make absolutely everything lighter. And if we can make things lighter, everything else becomes easier. And particularly if we can make things lighter while retaining the same strength and the same resistance and the same utility that they have right now. It's an issue with regard to building vehicles. It was an issue with regard to the single-stage to orbit vehicle. How could you make this thing light enough so that it could carry that much fuel and still be a practical vessel? It's a sort of thing that we have demonstrated in the past that our innovation is very, very good at taking things and making them smaller and lighter. And we still have room to grow in that department.
I may disagree with you.
Good.
Because I think that there is something that we can't shrink, and that is humans, right? So we need a lot of consumables for a long-duration space flight that we have to take with us. I mean, we never think about the volume and weight of consumables that we need in terms of anything. I mean, I'm just thinking about toilet paper, but don't pay attention to me. So just think about the number of food, water recirculation systems, the emergency systems that we need on board. And I think that because we don't have a limit in terms of volume and mass of a projected spacecraft for a long-duration spaceflight, I don't think we need to make it smaller. I'll feel more confident with a very heavy, sturdy, and huge fleet of spacecraft systems that will be able, if we have a problem, that surely we'll have problems in a long-duration spaceflight, we can have backup plans, because we won't be able just just stop in the corner and come back. So we are bound by the laws of orbital mechanics. So if we run into problems with our recirculation system or our water production system, or our food gets spoiled by some sort of a microorganism, we'll have to find our way. So I do think that we have to to produce a system. We are not bound by any particular weight or volume. But that's just my opinion.
Thank you very much.
Hi, good afternoon. I'm Eric Hintz. I'm an historian with the Lemelson Center at the National Museum of American History across the mall. And thanks, everybody, for a great panel. The comments about Laika and the Russian dog and its demise, I guess, led me to think about all of your talks. All are based on kind of an implicit assumption, which is we should take care of the human passengers, right? Whether it's the spacesuit or their habitability or just even getting them back to Earth safely without burning up. And it seems that you're all approaching it sort of from the U.S. perspective, but again, thinking about Laika, we've got the Russian space program, we've got the Chinese space program, presumably some other nations will come into human space flight, and so part of this is cultural. I'm curious if in your research, and this can apply to any of you, have you come across different attitudes towards what it means to take care of the human passenger? Are there like more rugged, less kind approaches to habitability or re-entry or spacesuits based on kind of a different approach or way of thinking about the passenger that may not be so kind?
Yes, I think there are. We can begin.
Well, all I was really going to say is, with the space program as it's been run as a government agency, having the conversation about not bringing the passenger back does not guarantee funding. So it's not really something it's not really an option.
Well, that conversation does take place,
Yes.
but they don't talk
Yes.
about that. That
There
is part of the
certainly as part of
worst case scenario.
And sending people who already have a very
One way to
fatalistic
Mars,
plan.
something like that?
Yes. I would agree with that. I think it's dangerous to assume that any one nation has a monopoly on humanity or humanism or the desire to keep people alive. But there are certain unique aspects of the American program in that it was made very open and very public very early on, which demanded a certain kind of sensitivity to how all of this would play on television. And particularly the perception that the United States was being cavalier about the safety of its astronauts was something that would not have been tolerated by any presidential administration. There's the lingering sort of suspicion that the Soviets were more hard-hearted about this sort of thing than they actually were. The idea that before Yuri Gagarin, there were at least one or two other cosmonauts who went up first and returned dead or didn't come back at all, which was a popular mythology for many, many years and to some extent still is. Not true, but it's something that bleeds into the public impressions people have about the respective space programs. It is true that if you want to imagine for yourself or for your nation a future in space, you have to solve the not dying problem, and it doesn't matter which country you live in.
Well, I can talk as a non-American citizen. I do believe that every country will like to have their astronauts back. Now, the degrees of roughness of the spacecraft and all the related systems, of course, that is very cultural, and it changes a lot. You probably, most of you saw in the news recently, after 520-something days, a group of people were locked in a can simulating a trip to Mars. And they did that I've been in the Institute of Biomedical Problems in Moscow. I saw the facilities that they were planning to put the people, and let me tell you, that is as Spartan as you can imagine. So a group of people were locked there, going nowhere for 500-something days. So I think that if you are going to Mars, you can take whatever, because you are focused and looking for the objective that is to go into Mars and come back, and you are prepared to take a lot of punishment in that goal. Of course, it will be nicer to have steak every day, but If you cannot, well, I'm ready to take it.